This presentation is called the Perma Pure Review of Humidity and Dew Point. So we're going to review the concepts of humidity and dew point and how we apply them to Perma Pure dryers and humidifiers. Let's start with relative humidity. Relative humidity is the amount of water vapor present in the air expressed as a percentage of the amount needed for saturation at the same temperature. The relative humidity represents how close the air is to saturation. It cannot be represented by a measured value. That's why it's called relative. Saturated air will have a relative humidity of 100%. For example, you need relative humidity of 100% to have rain form in clouds or water to condense. Because we don't Okay, I'm going to have to start this from the beginning. This presentation is called Review of Humidity and Dew Point. We're going to be reviewing the concepts of humidity and dew point and how we apply them to Perma Pure dryers and humidifiers. Let's start with relative humidity. Relative humidity is the amount of water vapor present in the air expressed as a percentage of the amount needed for saturation at the same temperature. In other words, the percentage of the water vapor that the water or the air at that temperature can hold. The relative humidity represents how close the air is to saturation. It cannot be represented by a measured value. Saturated air will have a relative humidity of 100%. For example, you need the relative humidity at 100% to have rain form in clouds or water to condense. The dew point is the temperature of air which is needed for condensation or dew at that particular temperature. If you take a glass of ice water and it develops condensation on the glass surface, the air on the glass has cooled to its dew point and the water vapor has condensed and created dew. The dew point can be used to calculate how much water vapor is in the air and can be represented by either a value in parts per million or as a pressure when using the atmospheric pressure as the standard. We use this as a representation of the actual amount of water in the air, or absolute humidity. Now, this is why Perma Pure uses dew point in all of its published performance data, because we could tie it back to an actual referenced amount of water. Let's look at the relationship between relative humidity and dew point. So in this slide, we will see with the cylinders present that the capacity of the air to hold water increases as the air is warmed and decreases as the air is cooled. So if we take air at 55 degrees and see the different cylinders as you go up to 80 degrees, you could see that the capacity of the air to hold water increases. The next slide shows the actual amount of water in the air that remains the same as the temperature changes. So if there's water present in the air and the temperature changes, and naturally the amount of water doesn't change. So once we overlay those two together, we can see the relationship between relative humidity and dew point and visualize the concept of relative humidity a little bit better. So at 55 degrees, you have a 100% relative humidity with that baseline. And as you increase the temperature, it can go all the way down to a relative humidity of 42%. That means at a temperature when it seems wet and it's absolutely humid, 25 degrees above that, it's going to feel dry. So just a short review of relative humidity. Given a constant moisture content or dew point in the air, as temperature rises, relative humidity falls, and as temperature falls, relative humidity rises. Now let's look at this graph. This shows how the dew point varies over a year. Now many of you are performing experiments or using atmospheric air as a purge gas in some fashion. We can see through this graph how the dew point varies at any given place in the earth over a year. So this is Rochester, New York, for example. You can see that not only does the dew point vary quite drastically within the month, but as the months progress, there is definitely a trend through the summer. The dew point rises through the summer and drops through towards the winter. This is a sinusoidal pattern that happens over the course of the year. If you're doing any measurements of atmospheric air, or you're using atmospheric air as a purge gas in some form, even if it's under vacuum, you will get some variability in your data. Now let's look at the relationship between dew point and relative humidity and how they vary over 24 hours. In this graph, the red curve is the temperature, the green curve is the relative humidity, and the blue curve is the dew point. You can see that throughout a day, the dew point doesn't really vary very much. But over the course of 24 hours, you have this sinusoidal effect where the dew point rises and falls in inverse proportion with the temperature. This gives a couple of interesting effects. Anybody that is working with measurement equipment outside will see that in many cases you might have dew that covers everything every morning. This could be detrimental to your measurements and your equipment. It also makes it very difficult when you're measuring particles, as the particle size is dependent to some degree on the relative humidity. This constant change in temperature and relative humidity makes any type of atmospheric measurements very difficult unless you try to correct that by drying the sample or keeping the sample at a constant relative humidity. It's also difficult when you have equipment mounted outside where the water can either damage a sensor or damage other electronics. In any case, the changes can also just give you variability in your data, and that's something that you'll want to see. We have many customers that have unwittingly found this variability when they understood how drastic these changes are throughout the year and throughout the day. So that concludes our presentation on relative humidity and dew point. Thank you very much for attending.